All right, so let's see if I can get in here real quick. So I actually did create the YouTube channel or playlist. Right now I've got last, or what was it, Tuesday's class loaded up on there. Um, I'll send you all the link for it so that if you do happen to miss a day in class or we went over something a bit too quickly for you, you do have the opportunity to go back and check it out. Uh, Unfortunately, I haven't figured out how to get our version of Canvas to actually host my Zoom stuff yet. When I do, then it'll be available through Zoom or through that Zoom link, although I'm not holding my breath on that one. And assuming that we can actually read things on the screen today, got a couple more sections to go over. For those of you that do anything with quality control or might eventually end up doing something with quality control, stuff we're going to talk about today can be useful, as well as the last section in here. We're going to be talking about how do you try to communicate some of the findings that we've had to other people. Just going to be honest. If you try sounding like a statistician when you're talking with people, they're not going to know what you're talking about unless you're talking to another statistician. So if you want to try to affect change or positive change in your workplace, uh, people need to understand what you're talking about, how you got your results, why what they want to do might not be the best thing in the world, and that sort of stuff. Uh, with the statistical quality control, there are some issues that actually come up with this if we're talking about it in terms of the real world. Uh, there is an option with Minitab to actually try to do uh, statistical quality control, uh, like plots and stuff like that. Sometimes, though, and we'll actually talk about it in a couple of minutes, the system that you're working with can't isn't good enough for, say, statistical or for quality control purposes. Quality control plots and all that, you can see it says, like down here, talking about acceptance sampling. You can run into issues where the company that you're dealing with needs a much smaller variability in the parts than you're able to offer. And we'll talk about some ways you can actually work your way around that without cheating, although it is really expensive to do that. But like most of the stuff in this class, again, there are going to be some of the definitions that we need to work on and deal with and understand. So it says acceptance sampling versus the detection approach. These two approaches are generally used for statistical quality control. Acceptance sampling is a technique in which a portion of the completed product is inspected. How many of you remember the binomial distribution from 301? Yeah. Last time I taught through a business school, I kept asking, so who remembers this? Do what now? Wasn't it chapter 3 of your textbook? Our professor didn't understand chapter 3, so they skipped it. Oh. So if we're looking at say this acceptance approach, one of the things we get to do is actually pull out our uh, knowledge of binomial or of the binomial distribution. If you remember it, great. If you don't remember it, uh, you'll get familiar with it again. But the binomial distribution, uh, it only deals with integers, and it can take values that range from 0 to whatever the maximum that you're dealing with. So if we're talking about, say, an exam in this class that's going to be worth 200 points, that max is going to be 200 points. If we're dealing with a say a 20-point quiz, then this maximum here is going to be 20 points. And to understand this, that maximum value that we're looking at, we're going to call that n. We also need some sort of a probability to deal with. For those of you that might be working in industry as, say, an intern or something like that, depending on the product you're making, depending on how quick or how expensive those products are, more than likely the probability, and this is going to be a probability of, say, having a defect, okay? Hopefully that's really, really, really low, okay? So let's say we know that 1% of the products you make are defective. Does anyone here actually have industry experience? Whether it's an internship or you might work with fruit at a particular grocery store. So if you're looking at, say, what percent of your fruit shipments are, say, moldy by the time they make it to the store, do you guys keep track of that?
Don't expect percent.
So we can use that as a screening thing. How many fruit does a typical store get in a day? Or if we're talking about, say, oranges or something like that that are being shipped to the store, 100 cases. So how many are in each case?
This is valuable.
So let's just say we're looking at batches of 1,000 parts. Okay. So a lot of times what you can do with this acceptance sampling is there's going to be a rule that says out of 1,000 parts, so like she was saying, less than 2% of them have to be defective. If we know that in general, 1% of your parts are going to be defective, we can go in, we can look at what is your acceptance range if we're going to look through all 1,000 of these parts if we wanted to, okay? So what is 1% of 1,000? Based on all of this, the expected number of, say, rotten fruit that are going to be coming in, based on what we have here, is going to be 10. So if we're going to check all 1,000 fruit before they go out on the store shelves, which depending on what grocery store you go to, they may or may not actually look before they put all that stuff down there. If we can get between 0 and if, So if 2% is bad, 20 would be 2%. So we need less than 2%. So we need to see what's the probability that we're going to get between 0 and 19 rotten fruit in our shipment here. Is this ringing any bells about how you use binomial distribution? Or is everyone still staring at that going, we did what now? The who, where? So, just based on what we have, if we get 19 rotten fruit or less, we're going to say, okay, we accept this batch. If it's 20 or more, we get rid of it. If we're using a graphing calculator, we can use the binomial CDF for 19, and that's going to give us a probability that we accept the material or accept this particular shipment. If we can go in, we can also look at what is the binomial CDF of 1000 minus binomial CDF, because 20 is our cutoff of 19. To give us the probability that we're going to, say, reject this. Because as you all totally remember from your 301 class, the probability an event happens plus the probability it doesn't happen has to be 100%, because it either happens or it doesn't. You can't have something that kind of happens. One of the examples one of my students gave was pregnant. You can't be kind of pregnant. You are or you're not. You don't, there is no in between there. So if we want to try to do that, if you have a graphing calculator, of course, since mine's software, I have to wait for it to actually boot up. If you have a graphing calculator, you can go second and then vars. Come down here to where it says binomial CDF and PDF. Is this ringing any bells for anyone yet? Bringing back horrible memories. So the CDF is the cumulative distribution function. The PDF, if I want to know what is the probability of getting, say, exactly 18 rotten fruit, I would use the PDF. If I'm interested in 19 fruit or less, so if I'm interested in a range, I want to use the CDF, which would be this one. And with this, I believe, put in the probability and then the number, and I have no idea why my calculator is doing it this way, because it's usually not that, which means if this isn't working right. So, all right, so that one's not working right. Let's try this other one. How many of you are familiar with Microsoft Excel? So with Microsoft Excel, you can actually use this in place of a graphing calculator if you need to. No, I don't. Oops. I don't need any of that. This is something that I give my students in my other stats classes. So what is the probability we're dealing with? 1%. How many samples or how many fruit are we going to inspect? 1,000. What is the high value we are interested in? That's going to be 9 or 19. And I might need to delete that. All right, that doesn't do anything. Cool. So the probability that we're going to accept uh accept this these 1,000 oranges or whatever it is ends up being 99.6668469%. If we have, say, a bad batch, and let's say 1.5% are defective, there's still, or rotten, there's still a pretty decent chance that they're going to accept everything. If we have, say, a really bad batch, let's say 3% of them are rotten, there's a 2% chance that your product is actually going to be accepted. So I don't know what the acceptance rate at Myers is, but
Very high.
so they must not have very many bad days. And if we make this, say, straight up 2%, there's actually less than a 50% chance that the entire batch of stuff is going to be acceptable. What's happening here is if we think about uh, binomial distribution, so we've got our 1,000 samples. So here's the probability that these things are going to happen. Out here, we're going to have 0 probability that all 1,000 fruit are going to be rotten, assuming that only 1% of the fruit are generally rotten. It's going to be very low. So what we're going to see is right around, right around the mean, or the expected number we're going to find. That's going to be the biggest part. It's going to come down. It's going to look kind of like the normal distribution, except it's going to have this really, 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 really long tail like that. So do you remember anything about dealing with long tails in your earlier class, or is that something we get to do here? Okay. So with data like this, we can use the mean, or we actually might want to try to use the median if we've done this quite a bit to try to figure out what's actually going on here. So in this case, I'm saying that we uh, accept all, or we inspect all 1,000 oranges that are coming into the store on a particular day. If you think about what happens with, say, Ford or GM or any place like that, they might get 1,000 engines into a plant in a day. Are they really going to inspect all 1,000 engines, tear each one apart to look at everything, then put it all back together? Hell no. So another thing that we can have is, again, let's say we're dealing with a probability that, or 1% chance that there's a defective part here. Since you can't generally look at all the parts that are going to be coming in, let's say we're going to select 50. Okay. Now, based on this, the expected number is still going to be, and do you all remember how to do an expected value from last class? The expected outcome is equal to n times p. Is that number, do you remember that one? Okay. So I guess there's a good thing we're going over it now. So just looking at this again, 1% of the items are going to be defective. We're going to look at 50 of them. What's 50 times 0.01? So that's basically telling us that we expect an entire lot to be rejected, or and in all one with the 50 items we look at, we expect essentially every other lot we look at will find one bad fruit or one defective part. So we can look at this. We can actually come back and say, if for our acceptance criteria, we'll accept it if we have 0 or one defective part, one defective or one rotten fruit in the 50 that we look at. We have 2, we reject it outright because that puts it at 2%. So based on what we've done here, how do we do this calculation? Again, we can look at the binomial CDF. For 1, that's going to give us the probability that we accept something. Because we've got the 2 numbers here, we could also look at what is the binomial PDF for 1 plus the binomial PDF of 0. And those should give us the exact same values. So now we can come in or come back to Excel. So we assume that there's going to be 1 or 1% is defective. We're looking at 50 samples now. And the high value here is going to be 1. And what do we see here? Based on what we're doing right here, we're only going to accept 30% of, say, all the pallets or all the shipments of fruit or whatever that are coming in, or all the parts. So maybe our criteria here is a little bit too strict. So you can actually bump that up to 2, see what's going to happen. And not much has happened there. See if we make that 5. Oh, let's see. Might have to get rid of that. Sorry about that. This isn't exactly perfect. My apologies. Going to go back to 1. That value, in this case, we're going to accept 91% of all the batches that we're looking at. This one should change based on values I have in here. Since I got rid of the value in there, it should actually delete itself. If we are interested in, or we will only accept it if we have 0 defects in the 50 we look at, you can see that we're looking at basically 60.5% of the acceptance. So when you're trying to do these calculations, you kind of need to know what is the potential for a bad part or rotted fruit? How many are you going to sample? What is a decent enough criteria? And if we're looking at 50 parts out of 1,000, and we have this 0 tolerance policy, basically you're rejecting 40% of everything that comes in. Anybody know what happens when your company rejects huge quantities of parts like that? Usually the company still pays for it. They just throw them away or get rid of them or whatever. So you bought them, but now you're trashing 40% of the stuff that you got. maybe you have too high standards. Maybe you have some definite issues there. Are so, and we'll talk about some of this other stuff that comes up too. And is this a lot clearer reading for everyone too? Like we can actually read things? Yeah, I had to bring my own document camera in. So another thing we need to look at when we're talking about quality control. And clearly, autofocus actually works on this one. There's what they're calling chance variation versus assignable variation. So why is uh, we're basically looking at what is the variability. Sometimes you can look at the system you're dealing with and you're able to go back and tell, oh, this machine's running a little bit hot, so it might not be cutting a part properly. So maybe we need to put fewer parts through that machine so it doesn't overheat. Uh, and sometimes things are just going to happen. It doesn't matter what you do, you're always going to get some bad parts or parts that don't work out too well. And you just can't do anything to prevent it. So you can think of this as preventable issues and unpreventable issues. The There's a stats class that I took called Design of Experiments. We're not going to be going over any of that in here, but we're looking at, say, variance total. In this case, variance that's assignable plus variance uh, due to chance. If we have everything working as well as we can, we hope that the variance or the variability that's assignable will actually be equal to 0. And then the variability that's equal to or due to chance, it's going to be whatever. Uh, we we might be able to do something about that too, but it might not be economically feasible. For example, you've got a machine that if you buy the brand new one, it's going to be $3 million, but your company only brings in $400,000 in revenue or profit every year. Can you buy a $3 million thing if you only have 400,000? And you also have to pay your employees and everyone else out of that money. So maybe sometimes that chance variability might be assignable, but it might be you might not be able to do anything about it. With a couple different uh, projects that I've actually worked on, uh, these usually end up being like say 50% each. In one case, it was 100% assignable, but the plant manager at this particular facility, we're so far behind, we can't stop to make things right. So we need to carry on with making literally 98% garbage. And so any accounting majors in here? Where are the accounting majors? Okay. Issue that all of us had where, and we're all engineers and scientists trying to figure this one out. Company pays, say, 3 dozen employees a decent hourly wage, benefits, all that other stuff. They also make the parts in-house. Then they paint the parts in-house. Then literally take most of the parts that were just painted, hire another couple people to take them out to the dumpster outside to throw them away immediately, and then hire a garbage company to come out and collect the garbage from two huge bins daily. Sometimes they need the company or the garbage company to come back a second time in the same day to again empty the two bins that were or replace the two bins that were there. That's how bad production was at this facility. And somehow they made money. Does that sound like a Enron scam going on there to anyone else, or is that just me? So uh, the reason why in this particular case it was 100% assignable was because we couldn't, uh, there's no way of telling what poor parts would, or how many poor parts were going to be coming out due to chance, because literally 98 to 99% of the parts got thrown away because uh, anyone that had an IQ over 6 could figure it out. But plant management clearly didn't have or wasn't that smart. Anyone here ever use the cans of spray paint before? I'm not saying did you go out and tag something or do any graffiti, just have you ever used a can of spray paint before? What do you find on the side of those cans of spray paint? There's usually a temperature range, right? Anybody know what that temperature range is for spray paint? Say like 70 to 90 degrees Fahrenheit. The facility we were at, uh, we had three lines of paint or three different paint crews on every single shift because the facility where they were painting was 130 degrees Fahrenheit to 150 degrees Fahrenheit. And if you've ever seen those car shows on TV where they're spray painting stuff, you have to be in the full, like the hood, the gas mask, the full body suit and all that. So imagine it's 150 in here. You've got all of that protective gear on and the goggles. How long are you going to last? They found uh, if you went more than an hour, people start fainting, and then there's paperwork to fill out. So your shift is 50 minutes. You then spend 2 hours sitting in a really cold room to bring your core temperature down, chugging Gatorade. Then after 2 hours, you go back in for 50 minutes of work and then go back and sit. While you're sitting, you're still being paid because it's not your fault the company was that dumb. But literally 99% of the parts they made were instantly disposable. I happened to be in the office with the quality control guy. His entire job, they failed. 60 grand a year. He had to stand up every once in a while. I want that job. So when we're looking at all these issues, like I was saying on the first day of class, does anyone remember the variability of the system? We can sometimes break it down into the different components or the different steps in the process that we're dealing with. That's where this comes in to be kind of handy. Uh, I used to be a chemistry or work as a chemist at a kind of local uh, chemistry lab. We were monitoring for uh, basically highly toxic substances. Uh, in our in soil and water samples. Uh, anyone hear of dioxin before? If you look it up, it's really nasty stuff. But what we're supposed to do is what we did as part of our quality control there is we actually had to create these quality control dashboards and quality control charts. We would intentionally inject all the samples that we were going to look at with a couple known uh, analytes that we could look at. They're not going to be in the sample. And then we would look at what was the reported concentration of these afterwards. If it works good or works well, what you should see is these things will just bounce back and forth. So might need to do this a little bit darker. There may or may not be, or there hopefully isn't any type of a pattern that we can see, but they all stay within certain ranges. And we're supposed to have it between 70% and 130% recovery. What we were actually getting was something more like that. So down here, 70%. Up here, it's 130%. So that last point right there, it's beyond our quality control chart or beyond the quality control limit. So we would say that the process is now out of control. The quality control manager that we had at this particular lab decided that if it's between the lines, everything's fine. Does anybody notice a pattern here with this last one? Yeah. And what we have down here is what we would call the run. So the first sample we ran, the second sample we ran, the third sample, fourth, and so on. Once we got to that particular point, uh, we needed to perform like quality control procedures to bring things back down. Basically, what was happening is the instrument we were using, uh, the thermal regulator on it didn't work all that well anymore. Because again, it was a machine from the 1980s and we're using it in 2010. Anyone here ever tried to buy really, really old computer parts that work? Good luck with that. With this particular instrument, in order to replace the part that was defective, it would have been $10,000 to $15,000, whereas a new instrument's $100,000. So clearly, the boss didn't want to deal with that, but they assumed, hey, if it's between the lines, everything's fine. Once we got it out of control, we probably actually have to go back and start running the last sample. We'd have to cool down the instrument, take about 2 hours, nothing else you can do. So, uh, how many of you ever get like a 2 hour lunch at work? Anyone? We would get 2 to 2.5 hours. When we had come back in, we'd rerun this sample, and magically it would be down at the bottom again. This sample would start that whole trend over again until we got out of control. Then might have to bring these down and do that over and over and over and over again. Which means if you had, because these samples could technically run by themselves, those all computer controlled stuff, you just had to make sure you labeled everything correctly in the computer as well as on the instrument. You could, if the thing worked right, you could literally go in the morning, hit the start button, go home, come back 8 hours later, your work is done for you. But because of the issues here, we'd have to look or check out the instrument, do constant vigilance on the instrument to make sure it's not screwing up too badly just yet. and your 8-hour workday with 15 hours of samples now becomes a 16-hour workday. You have a 2-hour lunch and a 2-hour dinner. So you only work 12 hours. You're only paid for 8 because you're salaried. And then you get yelled at in the morning because one, you weren't at the 7 a.m. meeting to hear how much you suck because you were at work until 3 in the morning trying to make sure or trying to get everything, all the samples run. And it's your fault that everything is bad. Anyone here ever hear of a toxic workplace before? That place was actually doubly toxic because it was chemistry, so we're also inhaling all sorts of nasty fumes at the same time. But anyway, so some things that can, or if we're going to be dealing with or trying to make one of these charts, we're going to have the upper control limit and the lower control limit. I'll just show you the formula that we've got here in the book. Do I expect any of you to memorize the formula? No. And when you look at this too, the upper and lower control limits are based upon what? The standard deviation here, right? And where does that standard deviation come from? That actually comes from the parts that you've actually been able to, say, produce. So you've got made, say, 100 parts, and whatever you have here in the middle here, that should be the average of those parts. And then based upon, again, upon the standard deviation that you got, or the variability of your ability to make those parts, you can actually have upper and lower control levels that are way, way far apart from each other. And then if you have something like this, where anything that's within 70% or 130% of what you know it should be is acceptable, it might be acceptable for you, or that might be the upper and lower control levels for your particular process. Does that mean it's actually going to work well for the company you're shipping parts to? Absolutely not. An issue, again, based on quality control that we had, was we needed, I was working at an adhesive or Ford Adhesives company in their R&D department. They needed the average strength of a particular bond to be within a range of, say, 40 units to 70 units. So as long as the average bond strength was within those regions, it's going to be perfectly fine. But they also needed the standard deviation to be uh, say below, and I don't remember what the actual value was here. Let's say 5. We were actually able to ship out parts or adhesive that would give a bond strength of 45. So we met this criteria here. When the engineer that was in charge of this went and looked at all the samples that we ran in the R&D department, he found, or he decided that the standard deviation was say 4.5. That's under 5. So that's also acceptable by the company's criteria. Okay. However, when we shipped or when they started getting the adhesives at the plant that or at the customer's plant, the engineers there were doing some analyses. So I'll say that was us. our customer was finding that the average was about 46, but the standard deviation was more like 5.5. So that fits with their goal. But according to them, the standard deviation for for what we were doing or based on their testing was beyond what they wanted. So we had to go in and the engineer that was in charge had to basically go in and argue with the company. And they spent, I think, 3 or 4 months going back and forth with each other, trying to figure out what's causing the difference here. Well, what was it? Here, uh, we had, say, n equals 9 samples. We actually ran, though, 11 to 13 samples, but the engineer would actually truncate that down to 9. So this average here was the average for the 9. The standard deviation was the standard deviation for these 9. Over there, they had, say, n equals 100 parts, and they ran 100 parts. So did you guys learn about something called a truncated mean? Okay. A common practice in engineering and sometimes or in engineering and science is you've got, say, 11, 12, 13 samples. Because you're running so many samples, you're going to get a good idea about what the average is. You're going to get a good idea about what the standard deviation is. But there is a chance that one of the samples might be uh, abnormally high or abnormally low. So in order to guard against that, you use what's called the truncated mean and the truncated standard deviation. So you're only going to take the 9 samples that are in the middle. Uh, Another place that uses this idea quite often is actually in the Olympics. If you've ever watched the Olympics, there are going to be, say, 7 judges watching the divers or whatever. And those judges are randomly assigned to basically watch whatever country it is they're going to watch. And say you're the Austrian judge and you're watching the Austrian diver. Do you think you're going to give that diver a little extra point or a few extra points just because they're from your home country? Well, because there were actually scandals where they found that sort of thing was happening, they'll actually look at, say, 7 judges, get rid of the high score, get rid of the low score, and take the average of the, say, 5 scores that are in between. They do it because they want to eliminate human bias. Because, like I was saying, if you're the Austrian judge and you got an Austrian diver and you're judging them, you're probably going to give them more points. Whereas, like, say right now, uh, if you're the Russian judge and you're judging the Ukrainian diver, you're probably going to give the Ukrainian diver less points than they deserve because they're Ukrainian, not Russian, and the other way around. So to get rid of those biases, they use the truncated mean. But the company, they don't care or they're interested in the outliers. They're interested in things that don't go exactly according to plan. So they're looking at all the data and they actually found that the standard deviation was too large. Once it was revealed the issue that was going on, we had to go back in the R&D department and try to figure out how can we reformulate the adhesive so that when the company gets it, it's actually going to be within their parameters for whatever it is that they are looking at. And I think it was right around that time when the contract I had was up. And ended up going to the other company I was talking about with the really bad quality control stuff. So apparently I have a history of working at companies with bad quality control. Anybody want to see how or want to talk about quality control when with teaching? Anyone? All right. So with the quality control issues, you can go back. Sometimes you can find a way to say minimize that variability. Sometimes you can go back and figure out how to make your parts say more acceptable to another company as well. So let's say again, we've got a process at our company where the average size of a product is going to be, say, 100. Uh, because we've monitored all the parts that have ever come off of these machines, let's say we know that the standard deviation there is 10. And if we want to try to predict the size of a part, so this is going to be the size of one part, we can basically use a 95% confidence interval. Formula that we're going to have here for these purposes is going to be mu plus and minus, should actually be 1.9683, blah, blah, whatever. I honestly don't care. I'm calling it 2 because I'm lazy like that. Times sigma. Plug in our numbers here. 100 plus and minus 2 times 10. So 2 times 10 is 20. So when we actually look at this, the parts coming out of our factory are going to be between, say, 80 and 120 in size. 95% of them are going to be within that range. But let's say our customer is only willing to accept parts that are in the range of 95 to 105. If you're working for the company that's making these parts, the customer that you're trying to sell to, that's their tolerance. So I have no idea if I spelled tolerance right. I think it's actually just got one L in it, but whatever. I'm not an English major, okay? I'm not an artist. And with how poorly I draw things, I hope you can all figure out why. But let's say you're working at this company. Can you sell parts to the customer here? We already talked about how we can do some of the sampling, and we can try to predict whether or not the company is going to say accept all the oranges or all the parts or whatever it is that our company is making. This is the range we expect all of our parts to be in. This is the acceptable range that the customer has. Should we be selling parts to this company? One of the things that we can do is if we pre-select the parts that we're going to ship to them. So we do have that option. Again, depending on what it is we're dealing with, the equipment could be fairly cheap in company terms, like say $250,000 to $500,000. Sometimes it could be as much as $10 million. And when I was an industrial engineering student, we had a retired quality control engineer come in and talk with us about some of the different issues that they had. If we're talking, since we're in Detroit, talk about automotive parts. They actually, rather than trying to figure out how to make the parts with smaller variability, smaller standard deviation, they decided that they were going to invest $10 million in a part scanner that would then assign parts to each other based on how defective they were to compensate for each other, so that when you put the two parts together, they'd be more likely to be accepted by the company they were shipping to. So who needs to make your part better when you can invest in how do we use the garbage we're making? These are all things that actually do happen. And I've got enough friends in the automotive industry. I know that it is still happening. So if we're dealing with with the customer like that, does everyone remember the normal distribution at least? Hopefully. So one of the things that you can have is if we have the normal distribution for the parts that are coming out of our manufacturing process. So again, the mean is going to be 100. So out here to out here, this is going to be 80. This is going to be 120. Everything within this range is going to be 95% of the products that our line or our company is able to make. Based on the tolerances here, that's going to be all the parts that the customer we're dealing with is actually going to be willing to accept. Okay. So going back to our to DS301, talking about the normal distribution, how do we actually calculate that? Again, we can use the normal distribution, the normal CDF. So we know that the average is 100. We know that the standard deviation for our process is that. The high level is 105. The low level is 95. And what this is telling us is that approximately 38% of the parts that we make are going to be accepted or acceptable to the company that we're dealing with. So since we are business majors here, along with an engineer, uh, should we be doing business with this company if we have to invest in a whole lot of equipment to make sure that we can get them the 38% of the parts that they accept? Should we be doing that? Another option, let's say we go back and we're looking at the variance, and uh, there's assignable variance and then there's a chance variance or random variance. Let's say we can minimize the assigned variance. We'll have to put forth some effort, but let's say we can get that down to standard deviation of 6. Now we find that, well, 59.5% of the parts we make here would actually be acceptable by the other company. So again, is this something that, an avenue that we would actually want to look at? Yes or no? How many of you are thinking about getting into the automotive industry at some point or working for an automotive company? Okay. One of the other things that came up, this was particularly true in the like 80s and 90s and a little bit in the 2000s. GM, Ford, and Chrysler at the time partnered up with Japanese auto manufacturers and started making, uh, essentially making American designed engines, but then American and Japanese plants would actually produce the parts that would go into cars. For example, Ford met up with Mazda. And again, dealing with the tolerances, so still talking about quality control issues here. So you got Mazda, we've got Ford. The average, so again, let's say it's 100 units or whatever, and we know that the tolerance level is between 95 and 105. So these are the parts that are going to be going into each of the cars. When you look at the Mazda made parts, they look something like that. When you look at the Ford made parts, they look more like that. Trash those. Maybe you can remanufacture those. But everything that's between these two lines here was acceptable. What ended up happening with the Ford made engines, the Ford made transmissions versus, say, the Mazda made transmissions? What And the same thing happened at, like, say, Toyota and GM. Same thing happened with Chrysler and Mitsubishi. What does everyone think about the quality of, say, or sorry, the reliability, I should say, of, say, a Toyota versus, say, a GM car, or of a Mazda versus a Ford? What's more reliable? Yeah, a lot of times the Japanese vehicles are much more reliable. Part of the reason is they go in, they try to make sure that or that their parts are uh, more uniform. And most of you probably weren't around for it. Like, how many of you were alive in the 90s and 80s? There were a lot of US companies that were pissed at the Japanese companies because the Japanese companies could sell cars here for that they imported from Japan for cheaper than the American car companies could sell them here. Couple of the reasons for that, the American car companies had to literally throw away so many parts that they made, so that's all wasted money. Uh, where does the money to throw these away or make these and then throw these away? Where does the money to make these and then possibly remanufacture them come from? Increased cost in the vehicles that you're buying. Because the variability of the American parts are so much greater than the Japanese, you're much more likely to have a warranty claim on a car, well, which costs the car company as well, which means they have to charge you more because you're going to bring your car in to need to get it fixed more often than some of the Japanese companies. So when you look at the price of the different types of vehicles, the Japanese cars were cheaper, even though they had to pay the import tax, even though they had to pay all sorts of other stuff, just because they were cheaper, not necessarily cheaper to manufacture up front, but uh, like the downstream cost, much fewer parts being thrown away, much fewer parts being made and then thrown away, or made and then remanufactured. That sort of stuff saved the Japanese company a lot of money in the long run, so they could sell their cars for cheaper, not because they were doing anything that a lot of the automotive unions around here thought was illegal. It's just they had better uh, manufacturing processes. Have things changed since, like, the 80s and 90s? Yeah. Are American vehicles a whole lot more reliable than they were in the 80s and 90s? Yeah. Are Japanese vehicles a whole lot more reliable than they were? Yeah. Uh, just as an example of that, talk with your parents about some of the cars they used to drive when they were teens. If their vehicle got over, say, 70 or 80,000 miles, they probably tried to get rid of it because they knew huge repair bills were coming. The last 3 cars that I've driven, it took 250 to 300,000 miles before the transmission went. So a lot better now than it was back then. So when we're trying to communicate these types of things, when we're trying to talk with other people, you can try to come in and sound highly technical. You can come in, you can start using all sorts of language that, say, upper management may or may not understand. And if you notice, what did I do with all of you today? I asked, do you remember the binomial distribution? I didn't say, you see, we can use the binomial distribution to blah, 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 because I've been teaching this class long enough. I know that some of you not going to remember stuff that's in the first class because that was how many months ago. So trying to make sure that you're using language that the people you're dealing with will actually understand. Make sure that you're using language and hopefully using useful pictorials. The charts that I just drew really quickly, I drew them really quickly because it would take more time to do it with Minitab if we tried to. Do we need, so if you're going to be given a presentation, by all means use Minitab, use R, use Python to make these. Some of the things that will come up as well when you're working in industry, they will have what are called dashboards and KPIs, key performance indicators. And a lot of the people at the top will check those things out regularly and use them to try to make decisions about what to do, what not to do. But how often do any of you ever look at a graph that someone made and go, huh, that's a thing that happened, and then you move on and you don't give it a second thought? Those higher ups do the exact same thing. So if you need to make the displays simple enough that whoever's looking at them can look at them really quickly and get an idea of everything that's happening. A lot of times too, the KPIs that they claim are KPIs are really just garbage. But they think they need them for something. Sometimes they don't. And one last little thing here. Another project that I worked on, we're looking at why are cars coming back coming back with the warranty repairs. So we're looking at the variance total. So essentially, what percent of vehicles will come back for an assignable cause? Versus what variance is random, meaning it's just going to happen. One of the other things, or what happened with this particular data set, and the talk that I'm giving to the math department is actually based a little bit on this data, and that's going to happen 2 Tuesdays from now. I'll make a post about it if anyone wants to show up for that. What actually happened here? The statisticians, the data analysts they had at a particular automotive company, because I had to sign like an NDA, so non-disclosure agreement. I can't say what automotive company it was, but you may or may not pass it while driving up I-75 in Auburn Hills. Not mentioning names. But they had a particular issue that they were trying to figure out, quote unquote, what are the drivers of poor vehicles, meaning what can you use any of the data that they had to figure out why vehicles were coming in for warranty repair. Got the whole data set, looked at literally all the vehicles. So this is one of the few cases where I had the entire population of data. And then I'm looking at it, and what I found was the date of manufacture was with that I was able to predict 70% of the warranty repair vehicles. Anyone want to give want to take a guess as to why dates of manufacture is so important for the quality of a vehicle? I'm sorry? Not necessarily the aging, because these were very specific dates. There could have been a batch problem. When I was taking that design of experiments class, the professor mentioned that always look at the date of manufacture because sometimes you have an issue with an entire batch of things. So that's a good thought. Anyone else want to take a guess? Or take a guess as to what dates or what days happen to be really, really poorly made vehicles? Go. Anyone else think that anyone else here slack off at work on a Friday? Could probably say the same thing about a Monday. Anyone go to work and at like say 8 a.m. on a Monday and you're completely recovered, you're not tired at all, and you're rip roaring ready to go? It actually wasn't a Monday or Friday. Uh, the date of manufacture for these vehicles was between Christmas and New Year. And if you know anything about automotive factories, when are they not operating between Christmas and New Year? So what happened was they had a bunch of vehicles they thought were faulty. They were going to check them out later, but they didn't have time to do it at the facility, so they just parked them off in like the corner of a lot and kind of forgot about them. Around Christmas, contractor came in and pulled them all out. And the date of manufacture that you see on your vehicles isn't necessarily the day it was made. That's the day it left the lot. Most of the vehicles, as soon as they roll off the assembly line floor, they get loaded onto a truck and then carted off to wherever their destination is. So when all these vehicles that came through as being a bad batch that was produced between Christmas and New Year of that year, how do you think the vice president for quality control took that when I told them about it? His entire staff of analysts were not able to figure this one out. I figured it out. Well, probably shouldn't say it while I was half drunk at 3 in the morning, because I was probably still mostly drunk at 3 in the morning at that point, but able to figure it out. And there was basically no doubt at all that it was these, say, this particular batch of vehicles. So I'll explain that to the vice president who's in charge of reliability and quality control for the entire company. While I'm giving my presentation to him, his fingers are going from tapping on the table to making a fist, and I'm afraid he's gonna like sucker punch me or something like that. He slams his fist on the table, points at the screen, those mothers something or others. Uh, it was literally the company they hired to fix the vehicles didn't fix them or didn't fix them well enough. So that was a $1 million or multi-million-dollar contract where they got money back on it. If I'd been an employee of that company, they do have a bounty program. Is anyone familiar with bounty programs at different corporations? If you come up with a process or a way to make a process run better, they will give you a percentage of whatever the, say, the new revenue is or the new profit is from that line. I showed the VP how to save the company literally a couple $1 million. What was my reward? What was my bounty? Good job. Have a mug from us. Had it worked for him, probably would have been 100,000, 150,000. So, but anyway, that's it for today. With the next set of stuff that we're going to be working on, I will post some data And we will be running through how to use Minitab to do different types of analyses. And we will be looking at what could be considered quality control at a university. And we can think of all the different professors that teach different classes at, say, the production facilities. That'll be fun. So have a good weekend. See you next week. I will post it on Canvas. When I post it on Canvas, it'll be an announcement, so it should get emailed to you. But there's also going to be the announcement thing online. So if you lost that email,
You know when you're gonna do that?
probably about 20
Oh,
minutes.
today. Okay, all right, perfect. Thank you.
This Minitab, I like accessing it like based on what the website says, but it's not like working. I don't know, like, do you have to buy it or is it part of our?
Because you're a student, staff, or faculty
Yeah.
at U of M Dearborn,